Hello APC Mechanics students in Unit 6 Oscillations, Class 3, 6.1 Simple Harmonic Motion, Horizontal Oscillator, Part 3. Now, in today's video, we're gonna solve some exercises on what we have explained so far. Then exercise 1, a block is hung vertically from an ideal spring. Notice that here the oscillator is vertical and not horizontal, but that won't change anything in the exercise itself. The block is pulled down and allowed to oscillate. The position y is a function of time for time t as shown in the graph above. Which of the following graphs best represent the acceleration a of the block as function of time? Now, whether it's vertical or horizontal oscillator, as we shall see in the coming classes, the differential equation that dictates the motion is given by minus kx is ma. Now here x is being treated by y, so minus ky equals to ma, which means the acceleration is given by minus k over m multiplied by the position, whether horizontal or vertical, that's the same, which means the acceleration is minus a constant multiplied by the vertical position. What does this mean? From this equation, if we have the position, the acceleration would be an inverted function with respect to the horizontal line and inflated. Now if you check carefully, the only function which is inverted with respect to the equilibrium line or this horizontal line is being given by choice A. Alright, B is also inverted. However, if you consider this peak should be located here. So this happens in this curve, but it doesn't work for B, so A is the correct answer. Now the graphs of position and acceleration as functions of time for an oscillating simple pendulum are shown. Even we didn't take what is a simple pendulum, however we can treat it as a simple harmonic motion for now. Now the magnitude of the acceleration at time t is equal to 1 second is most nearly. Now the position for a simple pendulum is given by theta and not x. However, in this exercise I'm gonna consider it to be x. Later on we're gonna introduce the variable which is theta. Now we need to find the magnitude of the acceleration at time t is equal to 1 second. If you look carefully at the graph, this corresponds for 1 second, this corresponds for 2, that's for 3, and that's for 4, which means this is also 1, that's also 2, and that's also 4. So they're asking for the value here, but notice that the graph, the labels are missing from the graph. So we need to determine that not graphically but analytically. Now first let's specify the period of oscillations. Now whether we are talking about position or acceleration, the period is the same. So let me use the position in order to determine the period. The period can be determined, okay, let me put again the labels. This is 1, that's 2, and that's 4, and that's 5. Now what does the period represent? The period is the time taken for 4 amplitudes. So basically this is 1, this is 2, this is 3, and this is 4. And we know that the period is being counted from the center. So we choose a point, skip a point, and choose another point. And indeed we have 4 amplitudes. Then basically the period is given by 4 seconds. Now in order to determine the magnitude of the acceleration at a specified time, you need to set the position time equation, then to determine the acceleration analytically. Now if you look carefully at the curve, and let's recall the sine and the cosine function. The sine function is something like that, and the cosine function starts from 1, oscillating. So you can notice that the position is being defined by sine function. So we can say that the position is given by an amplitude xm. Remember that here we're talking about the simple pendulum. So later on throughout the course, the position will be labeled by theta, but now for the sake of this exercise, you can consider it to be x. Now this is sine omega t plus phi. And because we are starting from the origin, then phi would be 0. So that would be xm sine omega t. Now the amplitude of oscillations in centimeters is given by 3. Now it's left to determine what is omega. Omega is 2 pi f, which is basically 2 pi over the period. And that would be 2 pi divided by 4 in the SI, and that would be pi by 2. So that is pi by 2 t. Now we need to find, or let me keep it as omega for now, because I need to apply the derivative. Now here, if we need to derive twice, then outside we will have omega square and with a minus sign. So the acceleration after deriving twice would be minus 3 omega square sine omega t. And now replacing t by 1 second, that would be minus 3. Now omega is given by pi by 2 to the power of 2 sine. Pi by 2 multiplied by 1. Plugging that on the calculator, the value would be given by minus 7.4, because the amplitude is being expressed in centimeters, so that would be centimeter per second square, and if you're interested in the magnitude, which makes B to be the correct answer. Now an object on the end of a spring of force constant K moves in simple harmonic motion with amplitude A and frequency F. Which of the following is a possible expression for the potential energy of the spring as function of time? We know that the potential energy is given basically by half kx squared. And now the position for simple harmonic motion can be either given by the amplitude, which is A, sine. Now omega is 2 pi f, so we're gonna represent it as 2 pi f multiplied by t. And if you notice that all of the following formats, they're considering the initial phase to be 0. This is one possible solution. Another possible solution would be given by a cosine 2 pi ft. So now let me go with the sine. Let's see if this works. That would be half k a square sine square of 2 pi ft. Now because the potential energy by its nature we need to have half k, so we can directly eliminate all of these, but we should have a to the power of 2 because it's x to the power of 2 and x is directly proportional to the amplitude, which makes a to be the correct answer. Exercise 4. An object on the end of a spring with a spring constant k moves in simple harmonic motion with amplitude a and frequency f. Which of the following is a possible expression for the kinetic energy of the object as a function of time? We know that the kinetic energy is given by half mv squared. Now if the position is given by a, so notice that we don't have the initial phase, so I will take the initial phase to be 0, and omega will be represented as 2 pi f. Then two possible solutions for the position are given by sine 2 pi f t, or even the position is given by a cosine 2 pi f t. So the first one, the velocity would be given by a, so let me represent 2 pi f to be omega. Okay, now you will notice why. So cosine 2 pi ft, and the velocity here would be given by minus a omega sine 2 pi ft. Now whether we're working with cosine or sine, that's perfectly the same. I'm just interested in the coefficient of the kinetic energy as we did in the previous exercise, so that would be half m. Let me go with cosine. That would be a omega cosine of 2 pi f t to the power of 2, which is basically half m a square omega square cosine square 2 pi ft, and I will ignore this part for now. Now notice that the mass doesn't appear in any of the choices, which means that we need to do some transformations. We know that omega is given by the square root k over m, so omega square would be k over m. For this reason, when I did the derivative, I re-represented 2 pi f to be omega because we're multiplying by the inner derivative. So that would be half m a square k over m with this trigonometric function m with m cancel. Then the coefficient that we're searching for is half a square multiplied by k multiplied by the bracket. And the only one confirms with this one is the choice B. Now a block on a horizontal frictionless plane is attached to a spring as shown above. The block oscillates along the x-axis with a simple harmonic motion of amplitude a. Which of the following statements about the block is correct? So at x is equal to 0, its velocity is 0. So if you notice carefully, they're trying to discuss the velocity and the acceleration. So let me state here, remember that when the velocity is max, the position is 0. When the position is max, the velocity is 0. So here let me say this is maximum velocity, this is velocity is 0, and that's velocity is 0. And let's start discussing all of these and doing some eliminations. At x equals to 0, the velocity is 0. That's completely wrong, because whenever the position is 0, the velocity is maximum, so I can directly eliminate this. At x is equal to 0, its acceleration is maximum. This is completely wrong. Why? Because the acceleration is given by minus k over mx. If the position is 0, the acceleration is 0, so we can directly eliminate that. At x is equal to a, its displacement is maximum. This is true because the amplitude corresponds for the maximum displacement, and it's healthy also to discuss these choices. At x is equal to a, the velocity is maximum. No, this is maximum position corresponds for minimum velocity, so that's wrong. At x is equal to a, its acceleration is 0. That's completely wrong, because when a is at its most, a is at its most. So that's wrong, which makes C to be the correct answer. Then let me write here again that the velocity here is max, the velocity here is 0, and the velocity here is 0. Now you can also think about it, why the velocity in this particular point is 0, because notice that initially if you're moving from points A to point B like that, and the block needs to change direction and move backward to the left, and this doesn't happen unless we know from the kinematics that the velocity momentarily vanishes. Okay, this is also one way to understand it. And similarly here, when block reaches this point and wants to return back, this doesn't happen unless the velocity vanishes momentarily. And remember that whenever we're talking about position, we're talking about elastic potential energy. Whenever we're talking about speed, we're talking about kinetic energy. A block on a horizontal frictionless plane is attached to a spring as shown above. The block oscillates along the x-axis with simple harmonic motion of amplitude a. Which of the following statements about energy is correct? Then let's discuss each and every one. A, the potential energy of the spring is at its minimum at x is equal to 0. Yes, it is true. Why? Because whenever we're talking x is 0, this is the minimum position, and that would give us the minimum potential energy, so A is correct. Now B, the potential energy of the spring is at its minimum at x is equal to A. No, A is max, which means US is max, so that's wrong. C, the kinetic energy of the block is minimum at x is equal to 0. No, actually, because the speed is maximum, which makes the kinetic energy to be maximum, that's wrong. Indeed, the kinetic energy of the block is at its maximum at x is equal to a. No, that's wrong. The speed is minimum, which means the kinetic energy is minimum. The kinetic energy of the block is always equal to the potential energy of the spring. No, that's wrong, because we know that there is always a continuous interchange between energies, kinetic and elastic potential energy. Now, a block of mass m is oscillating on a horizontal surface of negligible friction as shown in the figure. The spring is ideal, which means it's governed by Hooke's law, and in particular the period is given by 2 pi square root m over k, and the angular frequency is given by the square root k over m, and they only depend on m and k. When the block reaches the position x max, a left forward force that is external to the block spring system is applied briefly. Now we know that for a simple harmonic motion or horizontal oscillator, the block is left to freely oscillate. Now here what's happening when the block reaches this point, it will be pushed by a force to the leftward force. That won't change the nature of motion, but it will change the parameters or the variables of motion. Anyway, that is external to the block spring system is applied briefly. Which of the following best describes the effects of this force on the period and the amplitude of motion? Now, if you think about it, let's first discuss the period. Did we change the mass? No. Did we change the spring? So K didn't change. We didn't change M and K, so the period should stay the same. Which means we can directly think about either C or D. Now, if also when you push it by force, this would increase the energy of this oscillator, which makes it to oscillate with the greater amplitudes, making C to be the correct answer, because you have injected energy to our system and you didn't take any energy. As the block reaches this point and it's gonna move to the left, you're applying force in the same displacement, so which increases the energy. However, if the force was applied to the right, that would decrease the energy of the system, which makes then D to be the correct answer, but in this case it's C. Now, an ideal massless spring is fixed to the wall at one end as shown above. A block of mass capital M attached to the other end of the spring oscillates with amplitude A on a frictionless horizontal surface. The maximum speed of the block is Vm. The force constant of the spring is what? Okay, we will solve this exercise using two different methods. We have the mass, we have the amplitude, we have the maximum speed. We're interested in determining the value of K. And here we're considering its ideal, so we can directly use that the period is given by 2 pi square root m over k, and omega is given by square root k over m. So let me say that omega square is given by k over m. But we know that Vm is given by a omega. So omega in this case is given by Vm divided by a, and that would be V square m divided by a equals to k over m. And if you're isolating for k, then k would be given by capital M V square m divided by a, making D to be the correct answer. This is one way to solve it. Let me also demonstrate another way. Now we know that the energy of the oscillator is given by kinetic plus elastic potential energy, which is given by half mv square plus half kx square. Now you know that if there is no friction, so the energy is conserved everywhere and the spring will oscillate forever. Let's assume that. We can talk about two particular points given by the equilibrium and given by the amplitude. At the equilibrium, the position is 0, but the velocity is maximum, and the energy is given by half mv square m plus 0. Why? Because we know that the energy of any system is given by half mv square plus half kx square for a horizontal oscillator. If the position is 0, then the elastic potential energy is 0, but the speed is maximum, which means one form of the mechanical energy is given by half v square m. Now another form, when the position is at its amplitude, the speed would be 0, so the kinetic energy is 0, and all the energy of the system is given by half ka square. Now this is a form of mechanical energy, this is another form of mechanical energy, and this is another form of mechanical energy, and all of them are perfectly equal. Why we can equate all of them? Because simply energy is conserved. Now half cancels with half, and we're interested in determining k. Then if you isolate k, k in this case would be given by mv square m divided by a square, right? So this strategy is very important and will be discussed later in the coming class. A 2 kg mass connected to a spring oscillates on a horizontal frictionless surface with simple harmonic motion of amplitude 0.4 meters. We have the mass, we have the amplitude, we have the stiffness. The maximum velocity occurs when? So we know that the maximum velocity occurs when the position is 0, when the elastic potential energy is 0. Now when the potential energy is maximum, that's wrong. When the kinetic energy is minimum, no, because maximum velocity means maximum kinetic energy. When the displacement from the equilibrium is equal to the amplitude, which is 0.4 meters, no, because we said that the position is 0. When the displacement from equilibrium is half the magnitude, no, that's wrong, it should be equal to 0. When the displacement from the equilibrium is 0, which makes E to be the correct answer. And finally, the last exercise for today's video. Now the graph of one cycle of the displacement x as a function of time for a particle in simple harmonic is shown. Which of the following is the corresponding graph for velocity v as function of time t for the particle? Now initially, so we have the position versus time. We need to identify which one corresponds for the velocity. Initially the position is maximum, which means the velocity should be 0. Then we're limited either with b, d, or c. We can directly eliminate a, and we can directly eliminate e. And we can directly eliminate d because this is not the type of oscillations for velocity. we are left with either B or C. And here if you notice the slope, so at the beginning the slope is 0, but then the slope is negative at all points in the first amplitude, and the slope for a position time graph represents the velocity. Then in the first amplitude the velocity should be negative. Here in the first amplitude the velocity is positive, here it's negative, which makes C to be the correct answer. This is one way to know that C is the correct answer. Another way is try to construct the position as function of time. Try to derive it and check which one would be correct. Now we have two solutions, either sine or cosine. The sine function is something like that. The cosine function is something like that. So we can see that x is being modeled by a cosine function. Then we can write that x is given by the amplitude, which is xm cosine omega t. And here phi is 0 simply because we're starting like a cosine function, so phi is 0. Now if you derive it, that would be minus xm omega sine omega t, which is an inverted sine function. This is a sine function, and that's an inverted sine function, which makes again C to be the correct answer. Then thank you for watching, and see you soon in a new one.